All right, here we're going to talk about the chi-square equation and exactly how it's calculated and what all the little pieces mean. So here is a little graphic here showing you the actual equation. All right, this is the equation, and it's a test statistic. And what that means is it's a number that you're going to get. There's going to be an answer here, a number. And that number is going to tell you if your calculation is true or false in some way. In other words, it's a test to see if your results passed some type of shall we say, barrier to see if it's significant or not. And when I say significant, I mean the number that you get here, this answer right here, if it's above or below a specific value, all right, we're going to say something about your experiment. It's going to say my experiment means this, or my experiment doesn't mean this. All right, and that's what this is. This is a test to see if your experiment kind of passed the test of the results say what I want it to say, or the results don't say what I was trying to say. And what chi-square is specifically good at is testing to see if ratios are, how do I say it, close to one another, or they're vastly different. And so now that's not a good way to say it at all. It is about a ratio. It's about a ratio between two numbers, two sets of numbers. And if those two ratios are, they may not be exactly the same, but are they close enough for me to say that the results I got are close enough to what I thought they should be, that I'm going to go ahead and say they are. All right, so we're not saying that they are perfect. We're just saying that these numbers are close enough to the ones I'm expecting to say that we're going to say it works this way. Because here we have O and E. Let me just jump to that real quick. O and E stand for observed and expected. So we're expecting a particular type of number, or a set of numbers. We're expecting them. That's the perfect world here, these expected frequencies. But we're going to do an experiment, and we're going to get, actually, hopefully we get exactly these. All right. If we do, all right, then yeah, my observed are equal to my expected. So I'm going to say that everything is working exactly the way I want it to work. I expected something, and then I got what I expected. But maybe it's a little off. You know, you expect when you flip a coin for it to be 50% heads and 50% tails. But is it always? No, you can get off a little bit. Well, how far off do you have to get before you say, oh, this is not a fair coin. This coin does not give me 50% heads and 50% tails. And of course, there's the idea that if I flip the coin a lot, I should slowly approach 50%. So after I flip the coin, say 100 times, maybe I don't get 50 flips of a head and 50 flips of a tail. Maybe I get 47 and 53. The question is 47 and 53, if you're flipping the coin 100 times, is it close enough for me to say that, yeah, that's still a fair coin? And so there are tests to see if your observed frequencies, your experiment, the thing you actually did, like flipping the coin, fits your idea that that coin should give 50-50. So our expected in a chi-square, in our case, is of course going to be, we're expecting those ratios of, say, purple flowers to white flowers. We're expecting, let's say, a 3-to-1 ratio. And then we do the experiment, and we don't get exactly 3 to 1. Maybe we get 2.78 to 1, or we get 3.15 to 1. All right, something like that. Those ratios aren't quite exactly 3 to 1. All right, we don't get 3 purples to every 1 white. Well, is the number we got, the 2.78 or something to 1, is that close enough for us to say, well, it's close enough to our model that we are going to accept that we are actually working under this model? In other words, this model is a view of the universe. It's how we think the world works. The expected values are the values expected if the universe is actually working. If the world works the way we think it does, we should get, when we breed these plants, we should get ratios of, say, 3 to 1. But of course, it's not always exact. It's just kind of close to it, because there is some variability in there. Different things happen, and you can't control everything about the world and make everything work exactly the way you want when you do an experiment. And because of that, then we usually say, well, if you come close, it means that yes, it does work the way we think. It's just we can't control the environment well enough we can't control the experimental conditions well enough to get the exact result, but it's close to it. And that's what the chi-square does. It says, are my observed values close enough to my model of how I think the world works for me to go ahead and say that my experiment was a success and I did prove that we get what we are expecting. So this is what chi-square does, and it specifically tests ratios. It doesn't test, like for instance, we talked about the normal curve in another video. It isn't testing to see if our curve there is symmetrical. We're actually testing ratios, and that's like the ratios of our, say, purple to white flowers. And that's what chi-square is good for. So let's kind of move on a little more. Let me actually go here to and do a little experiment here. So we kind of understand the observed now, the results from our experiment, and the expected is a perfect world. Well, let's say we are expecting a 3 to 1 ratio. All right, so we're expecting, let's say we are expecting, we do our experiment 4 times or something like that. Let's just say we get the numbers 3 and 1. That's a ratio. All right, so maybe that's, if we're doing a bunch of them, let's say 3 to 10. That's still 3 to 1. All right, 3, you're expecting 3 from variable. Let's say these are the purple flowers. All right, we're expecting 30 purples to 10 whites, 10 white flowers. But let's say when we when we actually do our experiment, we don't quite get 30. We get purple flowers, and let's say we get 31 purple to 9 white flowers. Well, that's not exactly 30 to 10. That's not exactly a 3 to 1. But it is pretty close. And we would need to check that to see if that's close enough to our expected number to go ahead and say it is. And it's not exactly arbitrary, but we do kind of get the option of saying just how far off can we be and still accept it. And we actually set that ahead of time. Are we willing to say that we are willing to be wrong if we were testing this 5 times out of 100? That would be a 95% confidence that we got it right. Or maybe we're not we don't mind if it's off a little more than that, and we say, well, maybe we just need to be right 1 in every 10 times, so that would be a 90% confidence interval. But then let's say we want to be right 99 out of 100 times. Then we would say, well, we're going to increase the stringency of this model, and we're going to make it where you're only wrong 1 out of 100. That's 99% confident. Now, there are things like when you're an engineer, let's say, and you're working on working for NASA, and you're building a rocket, and you don't want it to explode. You have to get every little part right. You have to make everything work right. And when they do things like that, they actually make sure that they are correct. They're only incorrect 1 out of 1 million times. And that means there's a lot of zeros. It's not just 0.01, it's 0.000001. There are a lot of zeros out there, and so they want to get it so close to their expected results. They're testing a rocket, and they said, if we put in this much fuel, we should be getting this much thrust out of the back of the rocket. And they want to get it so close that their model says they should get a certain number, and they want to get it so close that they're only wrong 1 out of every, say, million tests, something like that. That would be very stringent. All right, so here in our case, we would need to calculate these types of things, and we're going to do some examples here in a second. But I just want to make sure this is the expected, all right, and this is the perfect world. This is what we do in our chi-square. We do the chi-square. This is what we do in our Punnett squares. We kind of come up with the perfect world. We cross the flowers and we say, oh, it's a 3-to-1 ratio. And then we go do our experiment and we actually count up the flies, or we count up the flowers, and this is what we actually got. And the thing is, how far off can we get before we say, nope, I think I did something wrong, I bred the wrong flowers, or the world just doesn't work the way we thought it did. These are not following the rules of Mendelian genetics, and that happens. All right, let's go back to our thing here. So I think you get the idea. Now, one thing we have to understand is, what is this symbol right here? This is called the summation symbol. It means the sum of. So we find the observed in the expected, and we square it, and then we divide by the expected again. So these are the same numbers. But what does this thing mean? Well, this thing means for each of your variables, do this, and then add them together. So it's the summation of you doing this a couple of times. But what numbers do you put in? Well, you put in the numbers for the purple and then for the white. So you can think of it this way. There are two E's. There's EP, and then there's EO. All right, and the expected, purple, LW, sorry. There's the expected for purple and the expected for white. There's also the observed for purple and the observed for white. So let's go back up here and figure out what these are. So the expected for purple is 30. The expected for white, is 10. The observed for purple, all right, is what, 31? And the observed for white is 9. So now what we need to do is put that into this equation. And we're going to put it in, we're going to run this equation twice. And the reason we're running it twice is because we have two variables. We have purples and we have whites. So we have to do it once for purple and once for white. If we had another color, then we would run it 3 times. And then we sum them up, we add them up, and that's what that big E looking symbol means, the summation symbol. So let's do it our first time. So we're going to do this for purples first. And so for purple, we would go, okay, our equation says, let's go back real quick, take the observed and subtract the expected. So take the observed. Where's my observed? All right, observed for purple is 31. All right, so put it in parentheses, and it's 31. And then we are going to extract what? Our expected, which is 30. All right, so now that we're going to have to square. So we just multiply it by itself, whatever that answer is. So I'm going to use this to say square it. And then we're going to take everything there, whatever our answer is. I'll put that in brackets to say that. And then we're going to divide by what? We divide by our expected. So EP is 30. So this is the equation for purple. Now what is our answer? Well, 31 minus 30, all right, is 1. 1 squared is 1 times 1, which still equals 1. All right, so then we take that 1 and then we divide it by 30. So our answer is 1 over 30, 1/30. All right, now we need to do the same thing for white. All right, and actually we can take kind of the same structure. I'll just copy this. But we're going to change the numbers because we're not using 30 and 31 anymore. We're using what? We're using 10 and 9. So our expected is this one, and our expected is 10. We're expecting to get 10, and we actually got 9. So again, 9 minus 10 is minus 1. So it's a -1 to the second. Now, of course, 2 minus 1 times minus 1 is positive 1. So we get the same answer. All right, and then 1 divided by 30 again. So our answer for both of these is actually 1 over 30. But that summation sign said we have to add those. All right, so we've done this twice now. So we've taken our we've run this for purple, we've run it for white, and we found the answer to this little equation. This says take those two answers and add them together. So that means in summation we go 1 over 30, oops, plus 1 over 30, and that's of course going to equal to 2 over 30, and that's going to equal to 1 divided by 15. So let's do our calculator here. Where's my calculator? Here we go. 1 divided by 15 is equal to 0.006 repeating. So 0.0667. So that equals 0. You get that right? Yeah, 0.67. I just couldn't remember if there was a 0 there when I did it. So that is our answer. And that's a very small number. Now here's something to remember. If you get it perfect, as in these numbers are the same, you got 30 to 10, and over here you got 30 to 10. What would you get? Well, you would get, as in, I'll just do it this way, 30 to 10 for both O and P, all right, if you get it perfect, all right, that means O and P are both the same ratios. So the ratio is 3 to 1. You got 30, you expected 30 of one color and 10 of the other, and you actually got it in your experiment. Then your chi-squared answer is equal to 0. All right, you're going to be subtracting here the same number. 10 minus 10 is 0, 0 squared is 0, 0 over 10 would still be 0. This is a perfect answer, and what that means is you hit the model exact, and whatever you were trying to say is correct. In other words, my hypotheses that we're going to talk about in a second is right on the model. In other words, our ratios are the same. All right, so realizing chi-square, when you do what's called your hypothesis and you come up with it, or your null or your alternative, whatever you're doing, realize you have to phrase it in terms of ratios. You have to do something that refers back to these ratios, because that's what the chi-squared does. The chi-squared, all right, tests whether or not these ratios are the same. And that's all it does. It doesn't do any more than that. All it can do is tell you, did my ratio come out close enough for me to say yes to the same model? If you get 0, it was exactly the same model. Now the question is 0.0667 close enough for it to say it's the real model? Well, the closer to 0, the better. All right? So the closer to 0, the closer you are to having the same ratios. Okay, that's all it's saying. Okay, that's all chi-squared tells you. It says if you get real close to 0, then you can pretty much say your ratios were the same. Now, how do we decide what's close enough and what's not? Well, that's where we go and we use some tables. All right, we use confidence levels. Well, we also have to decide, like I said, with the rocket and NASA, how close are we going to allow it? We can usually, highly confident is, well, we're willing to get it wrong 5 out of 100 times. Or we're willing to only get it wrong once out of every 100 times. Or in this particular case, 1 out of every 1,000 times. All right, now generally in biology, we'll usually go with this one, where you only need the 5%. And that's what we'll use in this class. And to do that, we need a table. We have tables that tell us what I call the magic number. It's a critical value is what the technical name is. And the critical value tells you, depending on how many variables you have, that's this, not quite this, but it's close to this. It's called the degrees of freedom. This is the number you have to be below. You have to be below whatever this magic number is, this critical value. Now, if we're only going to do where we're wrong 5 out of 100, so that's this one. But if we wanted it to make sure we were only wrong 1 out of 100, we would use this one. All right, so we're going to use this one, which is 3.841. So let's go back over here. And so the critical value is 3.841. And actually, that's not correct, because I just realized our degrees of freedom, we have we have two variables. We have a purple and a white, and you subtract 1. So how many, that's down here. The degrees of freedom are the number of phenotypes you have minus 1. So possible outcomes, all right, here is our degree of freedom. And so the number of outcomes in our case are, you can have purple and you can have white. That's it. All right, and then you subtract 1 from that. All right, so it's minus 1. That gives you your degrees of freedom. So how many degrees of freedom? 1. All right, so that means we need 3.841. And therefore, that is our number. We did have it right. So this is our number. If we go over that, All right. If you go over this, it means your ratios are too far apart. All right, and that means they're not, the numbers aren't close enough. You cannot say your data fits your model. All right, you said the world works this way and you're just too far off. So if when we did this and we got above a number above 3.841, well, at 5%, all right, at 5% being wrong, we're willing to be wrong 5 out of 100 times. And with two variables right here, the number we want is 3.841. And since we are below that here, we're actually okay with it. So in the above example, we are below 3.841. So we can say our model of the world, our model, or we can say our data, that's better. Our data fit is, what's a good way? So we can say our data is close to our model, and we can accept our hypothesis, or however you want to say it. I'm going to do another video just on how to state your hypothesis and things, because that's hard to do. So we'll do another video on how to state this fact that we got it below the number or above the number. You have to state things correctly, and you can't, and how to come up with that statement, the hypothesis, the null hypothesis, or the alternative hypothesis, depending on how you state it. You have to state it correct. So I'll do a whole video on just how to state it. But here are the things you need to know. You need to know how to do the degrees of freedom. You also need to know how to state the number of variables, or find out the number of variables, so that you can figure out the degrees of freedom. And then you need to understand that chi-square is just to see if these ratios, the ratios are like 30 to 10 or 31 to 9, how to test and figure out if those ratios are close enough or too far away for us to accept our world, the model of a world, or reject our model of the world, which is what your hypothesis is all about. Now let's see, I have another video. No? Yes, I explained that. All right, so that is chi-squared. That's how to use the equation and how to interpret it.